Hi everyone, this is your struggling CS student. Welcome back, and today let's solve another LeetCode problem. Let's take a look at today's problem of the day. 1769. Minimum number of operations to move all balls to each box. You have n boxes and you're given a binary string boxes of length n, where box I is 0 if the box is empty and 1 if it contains one ball. In one operation, you can move one ball from a box to an adjacent box, and box I is adjacent to box J if the absolute distance of I minus J is equals to 1. Note that after doing so, there may be more than one ball in some boxes. Okay. Why do they give us this as string then? They should just give it to us as an integer. Return an array answer of size n, where answer of I is the minimum number of operations needed to move all balls to the ith box. Okay. Each answer I is calculated considering the initial state of the boxes. Okay. In one operation, you can move one ball to each adjacent box. Okay. Let's take a look at example 1. So given boxes 1, 1, 0. Oh, I see, it's a string. Okay. The answer for each box is as follows. For the first box, you only need to move one ball from the second box to the first box in one operation. Second box, you only need to move one ball from the first box to the second box in one operation. And the third box, you have to move one ball from the first box to the third box in two operations, and move one ball from the second box to the third box in one operation. This is example 2. Okay, so what we realize is that in essence, for each box location, we want to know the distance between all the other balls to that position, right? So taking a look at this example 1, in this case, at index 0, what's the distance between the box location 0 and all other balls? So at index 1, there's one ball, and at index 2, there's 0 balls, so the answer is 1. And likewise for this case, so what's the distance between this box location to all other balls? And that would be what's that? There's only 1 here, and there's 0 here. And now the interesting case is when at box location 2, you have distance of 1 ball location at index 1, so that's 1. And then you also have a distance of 2 away from box location 2. You have 1 ball there, and that is there's 1 plus 2, and then you get 3. So initially, what I'm thinking of is monotonic stacks and queues, but maybe I'm overthinking this one, because in essence, for every box location, we want to query the distance, right? The distance from between the distance of all the other balls in one direction and all the other balls in the other direction, something like that. So that's just the initial thoughts. Is there other way that we can do this? Is there other way we can do this? Let's take a look at this one. Okay, let's take a look at this example. So at box location 0, we will need 1, 2, 2 plus 1, 2, 3, 4 plus 5. So that is indeed 11. Okay. So how do we calculate the distance between them? Oh, this might be a tough one for me. Let's see, 0, 0, 0, 0, 1, 0, 1, 1. So there's a smarter way of doing this. Maybe let's say we iterate from left to right. So 0, 0, 1, 1. Here's 2, here's 3. So this is just a prefix sum. But how can we use this information? If we can use this information, then we 1, 2, 1, 2, 2, 3, 3, 3. So at this point, let's say at this point, that means what? Okay, one thing, like, I'm not sure if this is it, but you recognize that this 3 plus 3, 6 plus 2 plus 2, that's 10 plus 1, that's 11. We actually get this. But is that the case for this one then? If you take a look towards the right, that will be, oh, sorry, is this one? So it's 5, 8. Oh my god, it's actually 8. I'm just noticing a pattern here, but I'm not sure what it means yet. This is 5. Looks kind of promising. Is this 3? No, that's 4. It's 4 because... Ah, okay. Or you calculate this one. But then you still have to iterate through, right? Then it's like, what's the point? Yeah, then it's like, what's the point? And in fact, this is not even correct. This is 5, 8 plus 3. Yeah. Okay, okay. Okay, yeah, maybe not. Okay, let's go back to the monotonic stack idea, because that's the only idea that I have right now. The distance, but when do we pop it though? When we see another one? Really? Okay. So let's say we build a monotonic stack from left to right. So in this case, it's 0, 0, 1. So I guess it has to be decreasing then. Decreasing. So 0, 0. And once we see a 1, right, and then it has to be, because it's decreasing, probably do a less than equal comparison, because we also want the answer for this one when we pop this off. So when we pop this, well, the distance between this is 1 operation. Distance between these two is 2 operation. Okay, so let's suppose this is our input. This is the monotonic stack, and this is our answer. Right, so our answer initially is 0, 0, 0, 0, 0, 0. Basically, the next time we see a 1, we want to know, well, and we are maintaining a monotonic stack, and we are popping off the top of the stack, then we can essentially calculate the distance between these two, and that would be 1. So let's say we increment this by 1, then increment this by 2, right? Now we maintain this stack here, like so. Oh, maybe I do it like this. Now we meet a 0, which is fine, but now we meet a 1 again. That means we have to pop it now. We have to pop it now, less than equals. So then we can calculate this distance for 1. Remove this, then put 1 back here. Huh. Okay. Suppose we go the other way around this time. Yeah, but we're still losing some information. Ideally, we can compute for this one, this distance, and this distance already. Currently, we only computed for this guy. Yeah, we only considered this one for this one. But if we don't maintain, what does that mean? If we don't if we don't allow duplicates, then it's 0, 0. Let's erase this. Let's reset this. 0, 0, 0. We don't maintain, and here, the next time we see a 0, we are already popping off. But we're not doing it, but we can't do anything. Okay, but let's forge on ahead. Decreasing, decreasing, now it's like this. This means what? We can pop here. We can pop this one and calculate the distance for this one. But then we're not calculating the distances for this. We're not calculating distances for this. Unless we can say for each index. So iterate from here and starting from here. Starting from here like this. What does this mean? No, but we already incremented though. We already incremented. Good. Can we do some sort of prefix sum instead? I was thinking like this would be index 0, index 1, index 2, 3, 4, 5. If somehow we can know the cumulative distance. Oh, the minimum number of operations. Oh, okay, I made a mistake. Okay, the one n is okay. The constraints. I should have taken a look at the constraints, but the constraint is 1 to 2000. So what does this mean? This means that n square algorithm might be acceptable. Maybe it might be acceptable. It's an n square algorithm. Well, if it's an n square algorithm, we can always, for each position, just calculate it like this. That's the n square solution. I'm not sure if there's a better way of doing this. I feel like there's a better way of doing this. But of course, the n square solution is trivial, right? Because for each box location, you're just calculating the left and the right. Always looking towards the left, always looking towards the right. Always looking. Huh. This is reminding me of like some sort of cumulative count. Some sort of cumulative count. But from the left to the right. So let's say if we maintain the prefix sum like this, 1, 1, 1, 1, 2, 1, 1, 2, 3. This is what? This has to move 2 distance. This has to move 3 distance. That's for this position though. Right? Yeah. 0, 0, 1. Oh, we have to move 1 distance here. Is it? 0, 0, 1. That's 5. It's 5. Wait, why is it 5? Oh, right, yeah. 1, 2, 3, yeah, it's 5. This is left to right. What about right to left again? 1, 2, 2, 3, 3, 3. At this position, that's a cumulative count. this minus this. Wait. This minus this. That will give me 6 though. That will give me 6. Wait, no. That will give me 5. I'm talking about. That will give me 5. And then we look the other way around. Do we have to look the other way around? This. If we look the other way around, this is left to right. This is right to left. So if we look the other way around, that would be like this. That's 6 though. Yeah, I'm stuck with this one. This is 6. What does it mean? Look towards the left. Take this minus this. No. No, if you want this, you just take this, right? Yeah. Okay. Okay. But from here, you look towards the right. And what's the sum of this? This is 3 plus 2, which is 5 plus 2, or 1 plus 1 rather. That's 7. But we know that this is what? The answer for this is 11. So for this is 11. We're just playing around the idea of looking to the left and looking to the right. Unless this is a DP problem. DP problem. I really don't think it's a DP problem though. Could be wrong, of course. Okay, if it's a DP problem, then how will it look like? That means that at every index, you could move the ball either to your left or to your right. You move the ball either to your left or to your right. I feel like brute force shouldn't work. I could be wrong though. Or is that actually what it meant? Let's play around with this idea a little bit more. A distance to your left. A distance to your left. How many balls are there? Okay, suppose there are one ball and one ball like this. 1, 2, 3. Then this is 3, 3, 4, and 5. 3, 4, and 5, right? 1, 2, 3, 3, 4, 5. Then at this particular position, now if you just look to the right and you get this sum, this is what? This is 9. Okay, 5 plus 4 plus 3, that's 9 plus 3, that's 12. Now, obviously, there's no 12th position because it's 1, 2, 1, 2, 3, so that's 5. Unless you deduct this, but 12 minus 2, that's 10. Look towards the left. You have 1 and 1, 2, which is correct, this one. Oh, wait a second. Wait a second. So maybe when you're looking towards the left, you care about the left to right array. When you're looking towards the right, for let's say at this index, you care about left to right. Oh shit. Maybe, possibly. So that means at this index, yes, you move 2 positions here. Or rather, we have 1 and 1, 2, so that's 3. And at this point, you move 5, right? Because it's 1, 2, 3, and then 1, 2. Oh, I think that has to be it, right? Yeah, I think that has to be it. Okay, let's do a dry run. Let's do a dry run. Yeah, that makes sense. Basically, at each index, when you're looking towards the left, you are counting like the displacement for each of the elements that are 1 using the prefix sum that goes towards right. So when you're looking to the left, it's a little bit confusing, but when you look towards the left, you care about the sum from left to right. When you're looking towards the right, you care from the sum from right to left. Okay, let's do a dry run for example 2, sample 2. So that would be 0, 0, and then erase this. So the cumulative sum from left to right, I'm just going to put this as left, this is right, and I means input, right? So the prefix sum from left to right is 0, 0, 1, 1, 2, 3. And then the prefix sum from right to left, that'll be 1, 2, 2, 3, 3, 3. So at this position, we want to look towards the left, the right, which means we care about the cumulative distance from right to left. Okay, now that makes a lot more sense. So what's the cumulative distance from right to left? That would be 6 plus 4 plus 1 is 11. Let's put the answer here. Let's put the answer here as A. So that would be 11 here. Now, let's take a look at this index. So for this index, we look towards the right. This means we care about this plus this. That would be what? That's 3, that's 4, that's 8, right? Hopefully we're still going strong. Yes, that's 8. Okay, good. Then now, at this index, we care about this one and this one, which is 5. Then we're at this index, we care about this one and this one. So that is 4. Hopefully we're still going strong. Yeah, we are. And at this index, we want to look at this and we want to look at this, right? So that would be 2 plus 1, that's 3. Then now, finally, at the last index here, to the right, we look at this. Well, there's nothing to look at actually. And to the left, we look at this. And that is 4. Is that 4? Okay, yeah, we got it. Yeah. Basically, to re-explain the algorithm, right, we maintain a prefix sum from left to right. That's represented by the left array. And then we maintain another prefix sum from right to left. That's represented by the right array. Right, the A is just our answer array. And at any particular index, let's say this particular index, right, when we are looking towards the right, this means we want the cumulative count from right to left. And when we're looking towards the left, we want the cumulative count from left to right. Because every time we add 1, let's say we encounter a 1 here from the right to left array, as we move towards a particular index, we are increasing its distance. Not rather we're like moving the ball from one location to the next, and we're tracking the. So if there was another ball here, then obviously we have to add the distance of the ball, because it's like as if we're moving two balls at once. So for this example here, move the ball here 1, 2, 3 times. It's kind of like this sum here. And then for this ball, we have to move it 1, 2, which is just like this sum. And that's the answer for this index. Okay, so that is the algorithm. Let's code it up. Oof. It was a tough one for me. You know what? There probably is some smart way of optimizing this such that you can make it constant space, but let's try to make it work first. So you have to left to right. Left to right is this, then right to left, like so. So we have to build this. So that'll just be your prefix sum. So boxes of 0, and then this is boxes negative 1. So here for I in range of 1 to the length of boxes, so let's put it as a variable n. Length of boxes. The answer we can build towards the end. Here, left to right dot append boxes of I, left to right -1 plus boxes of I. This is how we keep track the prefix sum from left to right, and now from right to left, I in range of n -2, -1, -1. Oh, maybe that's not the best way of doing this. Maybe we can do like this instead, times n, and right to left of -1 is equals to boxes -1. Yeah, maybe that's better. So so we need to maintain a cumulative count then. Count is equals to 0, or rather this boxes of -1. Then right to left of the previous guy, which is I plus 1 plus, or rather that's the count. We actually don't need the count here. Then we can just use the previous guy plus boxes of I, and that would be right to left of I is equals to this. Then we return answer here. Let's just take a look at the left to right and the left to right, and then you have right to left. Let's go at the array so that we don't make any careless mistakes. Oh, right. I need to convert them to integers. So I say boxes is equals to 1 for C in boxes. C in boxes, if C is equals to 1, L 0. Okay, what happened here? For C in boxes, if C equals to 1, L 0. Oh, this is wrong. Okay, fine. Let's say boxes copy. Is this still wrong? It's still wrong. Oh, yeah, dang it. Boxes copy is equals to this. Actually, what's wrong with my syntax? Yeah, let's find out what's wrong with my syntax. For C in boxes, L0, shouldn't be anything wrong with it. Syntax error. Damn, what's the error? Actually, don't know what's the error. Let's just do this the old-fashioned way then. Boxes copy is equals to this, and for C in boxes, and if C is equals to 1, boxes dot copy dot append 1, else boxes copy dot append 0. So here, boxes, here. Okay. So 1, 2, 2, 0, 1, 2 looks correct. Yep, that looks correct. Okay, so then we can build our answer array. So for I range of, maybe it's better if we do 0 times n, so that we already have all the indices ready to go. For I in range of n, we say answer of I is equals to, now we have to, maybe we can do count like left is equals to something and right is equals to something, and then the answer of I is just plus equals left plus right, right? Yeah. So the left would be, left is easy, right? Just left to right of I minus 1. Okay, but then you have to handle the 0 case. Maybe let's do left to right of I minus left. This means what? Left itself minus this. Okay. Left to right of I minus boxes of I. So this handles the 0 case as well, I think. Then it's right to left. Right to left. This time around, let's say is right to left of this minus this. So let's say we want this sum, that means this minus this. This minus this, you get this. This minus this, you get nothing, which is what we want. How about the maximal case? Maximal case, you take the whole thing, minus this current index, you have this. Oh, so you take here onwards, minus this. So you take here onwards, minus this. Okay. So it's right to left of I minus, wait, hold on a second. I think I still haven't processed it properly, right? I still haven't processed it properly. I think we need to process this again, right? Because at this index, answer here is, we look towards the right, is this and this one. Oh, right, we still have to process it. So this the processing is not done yet. Okay. Is it not done? It's not done yet. Of course, it's not done yet. What I'm talking about. Then for I in range of 1 to length of left to right, this means that left to right of I plus equals left to right of I minus 1. For I in range of n minus 2 of length of right to left of I plus equals right to left of I plus 1. And now you print left to right and right to left. Let's just take a look. Let's not do any calculation here. Oh, okay. Oh, let's see. Minus 1, and this is actually is length of right to left minus 2, right? Okay, now we get the cumulative count. Let's see if that's the case for this one. That's the one I know best. Yeah, looks correct, I guess. Okay, let's see. So then the prefix sum for this guy would be 0, 0, 1, 2, 4, and 7. Okay, looks correct. This one is 1, 3, 1, 3, 5, 1, 3, 5, 8, 8, 11, 14. Yep, that's correct. All right. So now for our answer, left to right is so at this position we want this sum. No, we want this one. All right, so we can just take this, right? I plus 1. Oh, but we have to handle the 0th case. Okay, so we take this minus this. Yes. Wait a second. Oh, smokes. Can we just add a 0 so it's easier to handle the 0th case? Add a 0 here, add a 0 here, something like that. Let's see. We want the sum from here to here. Well, this is the sum from here to here. So that would be this guy. But then, once we're at the end here, we don't want to go out of bounds. The left sum would just be what? Well, I minus 1, if that would be 0. You know what, let's just handle the cases explicitly. Let's not try to be too smart about this one. So we say left to right of I minus 1 if I is greater than 0, L 0, right? This one is I plus 1 if I is less than n, L 0. Is that it? Oh, snaps. Wait, what? I minus 1 if I is greater than 0. Wait, what's wrong with this? Less than equals, I guess. Ah, snaps. Right is right to left of I plus 1 if I is less than n. Isn't that correct? God damn it. Okay. I is greater than 0, then you do this, right? This one is if I is less than n. Between I and I less than n. Index 2, 0, 1, 2, oh, n minus 1. Okay, accepted. Quite confident for this one. So what's the time and space complexity here? The time and space complexity is O(n), where n is the number of characters in the boxes, string input, and the space complexity is up to O(n) because we are maintaining 2 perfect sum from left to right and right to left. Is that a constant space solution? Okay, let's try to submit this and let's try to upsolve it. Okay, we got accepted. I'm happy about this solution. But I'm pretty sure there's a way we can optimize this. Okay, so how can we optimize this, right? Okay, there's probably like a smart way of doing this, but in which you can get constant amount of space. But I feel like it's not worth it. I feel like it's not worth it. It's probably worth it, you can get a job, but it's hard, man. It's hard. What does this mean? Okay, let's think about it. Let's just spend 2 minutes thinking about it and see if we can think of the solution. If not, I'll just take a look at the editorial. So let's say at this particular position, do we know the count? We know the count to be this. We know oh, you know what? There probably is, but it requires overwriting the input itself. So you can store information in the input itself, and then that's how you can maintain constant amount of space. But then again, you have to modify the input list, which can be good or bad practice depending on your interviewer, because you never really want to modify the reference input, because that's just like bad practice, right? Yeah, it's bad practice because, well, a reference value has been passed to you and you modify the reference value itself, then when the client calls your code, uh, it it might not know that there's such side effect, and yeah, unless it's explicitly clear in your function description or your function name that the operation actually modifies the reference input. Otherwise, it's better to just make a copy of the reference input and then modify the copy instead and return the copy, just as a good practice in terms of software engineering. But so how would constant amount of space operation look like? Right, that's the question. That's the answer we want to know. So suppose we override the input itself. Oh, maybe we need this after all. Oh, we can use this as a reference. That means at this point, 1 is a 1, but then the cumulative count this time is also 1, and then now this one is 2, this one is 3. Okay. Now can we go the other way around? Can we go the other way around? Go the other way around. Not really. Maybe there isn't a constant space solution. Just thought that maybe there could be one, because LeetCode is always cracked on these kind of things all the time. So 1, 1, 2, 3. 1, 1, 2, 3. But I really lost this if you override it. It's not all you have is this. But how do you go from right to left and arrive at this solution? I don't think. Yeah, let's take a look at the editorial. Maybe there is a constant space operation, constant space solution. Okay, let me reset the code. Put the submission here. Okay, can't see everything, but just take a second to show the solution on the right. Okay, then let's take a look at the editorial. Oh, brute force. Yes, given that it is bounded by 2000, we can use brute force technique. Yeah, this is one of the solutions I was thinking of. You just brute force is n square. Is this accepted? Oh, I guess it's accepted if they say that's the case. Usually 2000 is still a little bit sketchy. I would say 5000 is definitely sketchy. 2000 you still can try to brute force and arrive at an n square solution. Sum of left and right moves, which is the idea that I took so long to think about. Ah, right. See, I freaking knew it. Of course, they have a constant space solution in single pass, no less. Okay, so you have the left pass and the right pass. Answer is boxes of 0, boxes to the left, move to the left, balls to the right, and moves to the right. Okay, single pass from left to right, moves to the left, balls to the left plus n of boxes I, moves to the left plus equals boxes to the left, balls to the left. The right pass, answer of J, moves to the right, balls to the right. Let's take a look at the description. If the target box is to the left of the ball, it will move left. If the target box is to the right of the ball, it will move right. So for each box, some balls will come from the left side and others will come from the right side. To calculate the distance for all the balls coming from the left in just one pass, we use a combined approach within a single loop. As we iterate through the boxes from left to right, we keep track of how many balls have been counted so far. Balls to the left. Each time we move on to the next box, the distance for all balls with the pass increases by 1. So the total number of operations for those balls increases by the number of balls we've encountered to the point. Yep. We also keep track of the cumulative number of moves to the variable of moves to the left. Fine. Similarly, we can calculate the distance for the balls coming from the right by iterating through the boxes from right to left. This is achieved by using the variable balls to the right to track how many balls we've encountered. Balls to the right. J. Oh, okay. So you just have a pointer variable here, pointer variable there. So if I, j, n minus 1 minus I. What the hell? Let's execute this code, see how it works. Oh, what happened? Oh, it's supposed to be like that. No. Ah, I see. Okay, that's smart. That's smart. Okay, I see what they're doing now. Basically, they have a pointer here, and then they have a pointer here, right? So that's the I and j respectively. So the left pointer will just go from left to right, and then the right pointer will go from right to left. And by the time it reaches the last index, it actually calculates like cumulative uh, number of moves needed to move all the balls from right to left. And this will be represented in this case, right? When you maintain a count from right to left. So it would be this one, this count. That would be 6 plus 4 plus 1 is 11. Ah, I see. Okay. Okay. Yeah. You see, I knew it. LeetCode always has some sort of cracked solution. Maybe this is not so cracked because maybe I just can't see it, but yeah. Anyway, that's the editorial for this one, and my solution for this, well, you have seen it just now. I'll just show it here again, just in case you want to see it. Here. Definitely took me way longer to solve this. I actually remember a similar problem to this one. I'll put the similar problem to the link in the description if you can find it. But if not, then yeah. Thank you for watching this. This has been a long one. Have a happy grinding.